welcome back. Now we start chapter 20. In chapter 20, one of the topics we're going to cover is specific heat, heat of fusion, and vaporization. So now I'll cover the theory, and then we'll do some examples for those. Okay, so the equation for heat transfer, H is equal to M times C times delta T. So this quantity C is known as the specific heat of a material. So let's see what that means. The H is the amount of heat that is coming into a substance or going out of a substance, right? So this one is measured in joules or calories, or it could be food calories. So the food calories, we write it with a big C, right? The mass of the substance is measured either in grams or kilograms, grams or kilograms, and then the change in temperature is usually measured in Celsius, right? Remember, when we have equations that depend on the change in temperature, we can use Celsius or Kelvin. So the change in temperature, we're going to use it in Celsius. So what is the units of specific heat? Well, the units of specific heat, depending on what units we choose for joules, or we choose calories or big calories, and then grams or kilogram. So it could be either of those. So the specific heat units are going to be either in joules per gram Celsius, or it could be in units of joules per kilogram Celsius, or it could be small calories per gram, small calories per gram Celsius, or it could be food calories per kilogram. So we would say big calories over kilogram Celsius. Okay, so what is the meaning of specific heat? So let's kind of focus on that, and then we'll give the specific heat of some substances, right? So this one tells us that the change in temperature of a substance resulting from that substance, heat coming into the substance or heat coming out of the substance, right? The change in temperature resulting out of that is equal to the heat divided by the mass times the specific heat, right? So for a given amount of heat flow, right? For a given amount of heat flow and for a given amount of mass, the larger the specific heat, the smaller the change in temperature, right? So the specific heat is measuring how much the temperature of that substance changes per given amount of heat flow and per given amount of mass, right? So let's say we have two substances. 1 joule of heat is coming into the substance, and the substance is 1 gram, right? So H is equal to 1 joule, and then the mass is 1 gram. Right, so this would be 1, and then this would be 1. Well, of course, then the bigger the specific heat, the smaller the change in temperature will be. Well, one of the things that we're going to see is that the specific heat of water is the largest specific heat of any material. So water tends to retain its temperature, and it's very hard to change it. Metals, on the other hand, have very low specific heats. So if they have very low specific heat, it means that their change in temperature is very high. So if they lose heat or if they gain heat, they quickly change temperature, right? So now let's give the specific heats of some materials. Other thing we could give is the conversion between 1 calorie and a joule, 4.184 joules. Okay, so that's the conversion. So let's see the specific heat of some substances, right? So specific heat is of water is going to end up becoming 1 calorie per 1 gram Celsius. Okay, so what does that mean? It takes 1 calorie of heat to change the temperature of 1 gram of water by 1 degree Celsius, right? It takes 1 calorie of heat to change the temperature of 1 gram of water by 1 degree Celsius, right? Or we can change that to food calories. 1 food calorie is 1,000 small calories. 1 food calorie, 1,000 small calories. So then we can multiply this by 1,000 and multiply the bottom by 1,000, and then we'll get 1 food calorie divided by 1 kilogram of water times 1 Celsius, right? So that would mean it would take 1 food calorie of heat to change the temperature of 1 kilogram of water by 1 degree Celsius, right? Then we can convert that to joules. Since one small calorie is 4.184 joules, 4.184 joules of heat to change the temperature of 1 gram of water by 1 degree Celsius, it would take 4,184 joules to change the temperature of 1 kilogram of water by 1 degree Celsius, right? Now let's see the specific heats of some other materials. The specific heat of mercury is going to be 140 joules per kilogram Celsius. So I'm gonna give it to you in these units, 140 joules per kilogram. So notice it takes a lot less heat to change the temperature of 1 kilogram of mercury by 1 degree Celsius, 140 joules, whereas water, it takes 4,184 joules, right? So the specific heat of mercury is a lot smaller, which means it's easier to change its temperature by 1 degree Celsius, right? The specific heat of steam, right? Steam is basically gaseous water, right? Water vapor. It's going to end up that the steam's temperature is easier to change than liquid water's temperature, right? So it's 2010 joules per kilogram Celsius. So it's about half of the specific heat of liquid water, right? 4,184 versus 2010, right? And then the specific heat of wood is 1,700 joules per kilogram Celsius, right? So wood is going to be easier to change its temperature than steam, but it's going to be a lot harder to change the temperature than mercury, right? Where mercury is 140. So then the specific heat of glass is going to be 837 joules per kilogram Celsius, right? The specific heat of ice is going to be 2090 joule per kilogram Celsius. Well, notice ice is similar to a little bit more than steam. So again, ice's specific heat is less than liquid water, right? Ice is pretty much solid water, right? So solid water and gaseous water's temperature are easier to change by about half as that of liquid waters, right? So that's kind of interesting. Liquid water has this interesting property that it doesn't want to change its temperature, but this is very important to life on Earth, right? That means oceans act as a buffer, so they don't change their temperature too high and they don't cool down too fast, right? So now we have a specific heat of aluminum. Specific heat of aluminum is going to be 900 joules per kilogram Celsius. So it's more than mercury's, but again, a lot less than water and a lot less than, well, it's a little bit more than glass, but it is a lot less than wood and ice, right? So aluminum is 900. The specific heat of silver is going to be 234 joules per kilogram Celsius. So now silver is going to be a little bit more than mercury. So you can see that the metals, aluminum, and silver, are going to be very, very small, and they tend to change their temperature a lot, right? So this gives you some examples of the different specific heats of materials, and then we'll do some examples of them. Now let's talk about heat of fusion and vaporization. Okay? F stands for fusion, and then V stands for vaporization. So fusion would be going from solid to liquid, or you could go liquid back to solid, right? Liquid to solid. You could freeze 1 gram of water and then change it to solid. You could melt 1 gram of ice and change it to liquid water, right? Vaporize is to go from liquid to gas, and then to go gas back to liquid. Okay, that's vaporization. You can interpret this various ways. To melt 1 kilogram of ice, it would take 333,000 joules of heat, right? 333,000. To melt 1 gram of ice, it would take 333 joules of heat. and to melt 1 gram of ice, it would take 79.6 calories of heat, right? So those are the various ways of saying it. So then, the heat of vaporization of water is going to be 2.26 times 10 to the 5th joules per kilogram, and in terms of joules per gram, it would be 2,260 joules per gram. And then if you divide that by 4.184, you get 540.15 calories per gram. So notice that to vaporize 1 gram of liquid water and turn it into steam, right, it would take 540 calories. So if you divide this 540 by 80, you get about 6 or to 7, right? So it's about 6 to 7 times harder to change liquid water into gaseous water as it is to change solid ice to change to liquid water, right? Well, what's happening? Well, to go from liquid to gas, you have to break the molecular bonds of the liquid a lot more so that it turns into gas, and then the molecules are not connected to each other anymore, right? But when you're going from solid to liquid, you don't have to break the molecular bonds as strongly, right? The solid is a crystal structure, and liquid, they're still pretty much bonded together. Gaseous molecules, they're basically free to roam, right? So it's a lot harder to change from liquid to gas as it is to change from solid to liquid, right? Now we can state the heat of fusion of other materials. Heat of fusion of lead is going to be 2.45 times 10 to the 4th joules per kilogram, right? So this is to change solid lead into liquid lead, basically to melt lead, right? 2.45 times 10 to the 4th. Oh, so that's interesting. It's actually easier to change lead to liquid lead than it is to change ice to water, right? It's 2.45 times 10 to the 4th joules per kilogram, right? Now, LV of lead, to change liquid lead and change it to gaseous lead, then that's going to be 8.70 times 10 to the 5th joules per kilogram. Seems to follow a pattern too. So it's actually easier to melt silver. Once you reach the melting point of silver, it's easier to melt it than water, right? 8.82 times 10 to the 4th. But once you reach the boiling point of silver, 2.33 times 10 to the 6th, that one is even harder than to boil lead. Lead was 8.70 times 10 to the 5th, and then silver is 2.33 times 10 to the 6th. So it's very, very high. So there does seem to be a pattern there. One other example we can say is F aluminum, 3.97 times 10 to the 5th joules per kilogram, and then LV aluminum, 1.14 times 10 to the 7th joules per kilogram. So let's see, 3.97 times 10 to the 5th, that one is actually more than water, right? So that kind of broke the pattern. So at 3.97 times 10 to the 5th, slightly more than 3.33 times 10 to the 5th. So I like looking at numbers like this and seeing if there's patterns, are they ever broken, or are they consistent? Well, they were consistent for lead and silver, but then when you got to aluminum, 3.97 times 10 to the 5th, you can see that it's slightly higher than water, right? But the LV of aluminum, 1.14 times 10 to the 7th, that's off the charts, basically. This is 10 to the, silver was 10 to the 6th, lead was 10 to the 5th, and then aluminum is 10 to the 7th. So it's a very interesting topic, looking at these numbers, comparing them, and seeing if there are patterns. Okay? So next we'll do some examples of problems that utilize these quantities, okay? Thank you very much.